Welcome back to our ongoing exploration of the OEIS.
The online encyclopedia of integer sequences.
Right. Today, we're diving into sequence 00000069,
Okay.
a set of numbers with a rather peculiar name, odious numbers.
Odious number.
Yeah.
What makes a number so odious?
Well, it all comes down to their binary representation. An odious number has an odd number of ones in its binary form.
I see.
For instance, the number 7,
Okay.
which is 111 in binary, is an odious number.
So the number of ones determines whether a number is odious or not?
Exactly.
What happens if a number has an even number of ones in its binary form?
That's where the evil numbers come in.
Evil number.
Yeah, they make up the complementary sequence A00019969.
Okay.
And they have an even number of ones in their binary representation.
So 6, which is 110 in binary, would be considered an evil number.
Exactly.
Interesting. So we have this fundamental division of non-negative integers based on their binary structure.
Right.
The odious and the evil. Does this distinction lead to any interesting mathematical properties?
It absolutely does. One fascinating property lies in the sums of pairs of odious and evil numbers.
Okay.
The Lamberk and Moser theorem states that if you split the non-negative integers into odious and evil numbers, you end up with two sets that have identical multisets of pairwise sums.
That's a surprising outcome.
It is.
So if I were to take all the possible pairs of odious numbers
Right.
and calculate their sums and then do the same for all the pairs of evil numbers,
Yeah.
the two sets of sums would be identical. That's not what you'd intuitively expect just by looking at the binary representations.
You're exactly right. It highlights a hidden symmetry in the seemingly simple distinction between these numbers. It suggests that the arrangement of ones and zeros in a number's binary representation has implications for its behavior in additive operations.
No. This binary perspective reminds me of another intriguing sequence, the Thoomor sequence.
Yes.
Does it by any chance have a connection to our odious numbers?
The positions of the ones in the Thoomor sequence correspond exactly to the odious numbers.
So like a hidden code where the Thoomor sequence acts as a map
Exactly.
pointing to the location of each odious number?
Precisely.
That's fascinating. Two seemingly unrelated concepts linked by their binary structures.
Yeah.
This connection certainly makes you wonder what other hidden patterns might exist.
Speaking of patterns,
Yeah.
did you know that every power of 2 is an odious number?
Let me think about that for a second.
Okay.
A power of 2 in binary always has a single 1 followed by all zeros.
Right.
So yes, that would inherently make them odious.
Exactly.
It's a direct consequence of their unique binary structure.
And this binary peculiarity extends to another famous family of numbers, Mersenne primes.
Mersenne primes.
With the exception of the number 3, every Mersenne prime is also an odious number.
Ah, yes. Mersenne primes being of the form 2p1, where p is prime,
Right.
have a binary representation consisting of p consecutive ones. So unless p is 2 giving us the Mersenne prime 3, they will always have an odd number of ones and therefore be odious.
The OEIS entry also presents a curious mathematical formula related to odious numbers.
Okay.
AAN equals 2AN, where AN represents the nth odious number.
What does this formula tell us about the behavior of odious numbers?
It means that if you take an odious number, find its position in the odious number sequence, and then find the odious number at that position, you'll always arrive at twice the original odious number.
Okay, let's try an example to make this clearer for our listeners.
Sure.
Take the odious number 1.
Okay.
It's the first odious number in the sequence.
Right.
If we apply the formula AA1, we get A1 equals 2, which is indeed twice our original number.
Yes.
Another example. Take the odious number 5, which is the fourth odious number in the sequence.
Okay.
Applying the formula AA4 must 2A4, we get a 4A10.
Right.
So the fourth odious number in the sequence, 5, when doubled, gives us the odious number in the fifth position of the sequence, which is 10.
Exactly. It's like a numerical echo within the sequence.
Quite intriguing. This formula suggests a deeper self-referential structure within the sequence of odious numbers.
And to add one more fascinating fact to the mix, the OEIS entry mentions an upper bound on odious multiples.
Okay.
For every positive integer n, there's an odious multiple that's at most n plus 4.
Does this bound hold true for all numbers, or are there specific cases where it's particularly relevant?
Well, it turns out that this bound is tight for Mersenne numbers with even exponents.
So for these specific numbers, the smallest odious multiple you can find is exactly nn plus 4.
Precisely.
That's quite a specific connection. It suggests that the properties of odious numbers are intricately linked with certain types of numbers, like Mersenne numbers with even exponents. It makes you wonder what other relationships might be lurking beneath the surface.
It certainly does, and this connection highlights the value of exploring number sequences like this one. They can reveal unexpected relationships and offer new perspectives on familiar mathematical concepts.
Indeed. It's a reminder that even seemingly simple definitions can lead to a rich and complex mathematical landscape.
So we've uncovered some fascinating properties of odious numbers just from the OEIS entry itself.
Yeah.
But I'm curious to see what other insights we can gain from the research and references mentioned.
That's a great idea. A deep dive wouldn't be complete without looking at the scholarship surrounding the topic.
Right.
It's like exploring a new land.
Okay.
You start with a basic map, but then you need to consult the experts to understand its hidden treasures.
I like that analogy. So the OEIS entry lists a variety of research papers and books that delve deeper into odious numbers and related concepts.
Okay.
For instance, there's a paper titled Beyond Odious and Evil by Alush, Kloiter, and Shevelev.
Beyond Odious and Evil. The
Right.
title itself suggests that there's a whole universe beyond the basic definitions we've discussed.
Right.
I'm curious to see what they uncover beyond the odious and evil.
Me too. There's also a paper listed titled Additive Number Theory via Automata Theory by Rajasekharan, Shellett, and Smith.
Additive number theory via automata theory.
Yeah, it explores how computational models can be used to study problems in additive number theory.
That's an interesting connection.
Yeah.
It suggests that we can use computational tools to gain a deeper understanding of the additive properties of odious and evil numbers.
Exactly.
It's like using a powerful lens to see patterns that might be hidden to the naked eye.
Precisely. And the Wikipedia article we have also highlights some interesting points.
Okay.
For example, it emphasizes that the way we partition non-negative integers into odious and evil numbers is unique in a very specific way.
Right. It's the only way to divide these numbers into two sets,
Yeah.
where the multisets of pairwise sums are identical.
We talked about the Lamberk and Moser theorem earlier,
Yeah.
but the Wikipedia article emphasizes the uniqueness of this partitioning.
Let's think about this for a second. Imagine if we tried to divide the non-negative integers into two sets based on some other criterion.
Right.
Would we still get this property with the pairwise sums? Most likely not. Exactly. The fact that this property holds true only for the odious-evil partition makes it even more remarkable.
Right.
It highlights the special nature of this binary classification.
And the Wikipedia article also provides a specific example to illustrate the formula AAN equals 2AN, where AN is the nth odious number.
Okay.
It uses the odious number 4, which is the third odious number in the sequence.
So if we plug in 3 for n, we
Yeah.
get AA3 equals 2A3.
Yeah.
Since A3 is 4, this becomes A4x 8.
Right.
And indeed, the fourth odious number in the sequence is 8, which is twice the original number.
It's a clear demonstration of how this formula creates a sort of recursive echo within the sequence.
Yeah.
You apply the formula once, and you jump to another position in the sequence that's related to the original number in a very specific way by doubling it.
And the Wikipedia article also reminds us of a key property we discussed earlier.
Yes.
Every power of 2 is an odious number.
Right, because their binary representation is just a single 1 bit
Yeah.
followed by all zeros.
Exactly.
This ensures they always have an odd number of ones.
Yeah. It's a simple yet elegant connection between a number's value and its binary representation.
And this binary characteristic also extends to Mersenne primes,
Right.
except for the number 3.
Yes.
Remember, Mersenne primes are prime numbers of the form 2p1, where p is also a prime number.
Yes, and their binary representation consists of p consecutive ones.
Right.
So unless p is 2, they will always have an odd number of ones, making them odious.
It's amazing how the simple act of looking at a number in binary reveals these connections between seemingly disparate concepts powers of two Mersenne primes and odious numbers.
It's a reminder that changing our perspective can often lead to new insights.
The Wikipedia article also reminds us of the upper bound for odious multiples.
Right.
Every positive integer n has an odious multiple that's at most n plus 4.
And this bound is tight, meaning it's the smallest possible bound for Mersenne numbers with even exponents.
Right.
This further strengthens the link between odious numbers and this particular family of numbers.
It makes you wonder if there are even deeper connections waiting to be discovered.
Absolutely. Both the OEIS entry and the Wikipedia article offer numerous links and references for those who want to delve further into the world of odious
Yeah.
numbers. These resources provide a wealth of information for anyone interested in continuing the exploration.
It's like we've given our listeners a starting point for their own mathematical adventures.
Exactly. We've provided the map, and now they can choose their own path through this fascinating landscape of numbers. So what can we say about odious numbers now that we've explored their properties and connections?
Well, for me, it's a reminder that even seemingly simple mathematical concepts can hide a surprising depth of complexity and connections.
Okay.
Odious numbers, with their simple definition based on binary representation, have led us to explore ideas from additive number theory, the Thoomor sequence, Mersenne primes, and more.
It's a testament to the interconnected nature of mathematics.
And it makes you wonder what other seemingly mundane mathematical concepts might hold hidden depths waiting to be uncovered.
Perhaps our listeners will be inspired to embark on their own deep dives into the world of numbers.
It's amazing how much we've uncovered about odious numbers, starting with just their definition.
Yeah, it really is. It's a perfect example of how a simple concept can open the door to a rich and complex mathematical world.
Exactly. So, as we wrap up our deep dive into A000069, let's take a moment to summarize the key takeaways for our listeners.
All right, let's recap. We began with the basic definition of an odious number: a positive integer with an odd number of ones when expressed in binary.
And we explored how this simple binary characteristic distinguishes them from their counterparts, the evil numbers which have an even number of ones in their binary representation.
This seemingly straightforward distinction led us to the Lamberk-Moser theorem, which reveals a surprising symmetry in the world of numbers.
Yeah.
It states that the multisets of pairwise sums for odious and evil numbers are identical, highlighting an unexpected connection between binary representation and additive properties.
The fact that this partition is unique, the only way to split the non-negative integers to achieve this property, makes it even more remarkable. It suggests there's something fundamentally special about this binary classification.
We then discovered a fascinating link between odious numbers and the Thoomor sequence, a sequence famous for appearing in diverse areas of mathematics.
Yes.
It turns out that the odious numbers mark the positions of the ones in this intriguing sequence, connecting these two seemingly disparate concepts through their binary structure.
And let's not forget the inherent odiousness of powers of two textramers. Their binary representation, a single one followed by all zeros, makes them perpetually odious. And this binary peculiarity extends to Mersenne primes as well, except for the number 3, as their binary forms consist of consecutive ones.
Then we delved into a recursive formula that describes a fascinating pattern within the sequence of odious numbers. N equals 2an. This formula demonstrates a numerical echo where applying it twice leads you to a multiple of the original odious number.
Right.
It highlights a deeper self-referential structure within the sequence itself.
We also touched upon the upper bound for odious multiples. Every positive integer n has an odious multiple no greater than n plus 4. And this bound is tight for Mersenne numbers with even exponents.
Right.
This connection strengthens the link between odious numbers and this specific family of numbers, suggesting a deeper relationship worthy of further exploration.
We've covered a lot of ground in our deep dive today, but this is just the beginning. The research papers and resources listed in the OEIS entry and the Wikipedia article offer a wealth of information for those who want to continue exploring the fascinating world of odious numbers.
So to our listener, we leave you with a challenge. If such a simple definition can lead to such a rich tapestry of mathematical connections, what other hidden depths might be lurking within the vast landscape of numbers? We encourage you to explore, to question, and to continue your own deep dives into the intriguing world of mathematics.